In this video, we're going to look at our first examples of wireless power transfer. These will lean on the relations between fields and inductors and capacitors that we saw in Maxwell's equations. The first kind of wireless communication that we're going to run into is called capacitive coupling. The picture on the left shows a good model of capacitive coupling. We've put a metal stick in the electric field formed by a capacitor, and we'd like to know how much voltage appears on the stick. Maxwell tells us that the field starts and ends on charge, so each set of field arrows must imply the buildup of charge as we apply voltage, in other words, a capacitor. That means we can represent our stick in a field as a capacitive divider. And we can find the voltage at V out by writing a standard impedance divider equation. Note that the frequency dependence of impedance falls out of the equation, so this coupling behavior works at almost all frequencies. Though it is pretty weird at low frequencies because every impedance is infinite. So this is mostly useful for transmitting or observing high-frequency electric fields. There are lots of potential examples of this in the world. I've included a cheeky one where someone left a fluorescent lamp dangling near power lines, and it lit up because of the electric field coupled onto it, though magnetic fields around the lines probably helped with the coupling too. This picture contains one good insight for circuits, which is that your field lines terminate all over the place, especially if you don't care to build PCBs or breadboards that confine them carefully. In this case, some electric fields from the lines terminate on earth ground, by which I mean the actual ground that you stand on the earth. We can see an example of how that affects us in PCBs in the second picture I've included, where an aggressor trace on a PCB drops some electric field onto a neighboring wire. The second kind of coupling that we need to discuss is inductive coupling, which arises because of the relationship between current density and the curl of magnetic fields. If we run a current through the lower coil of our left picture, then a field must exist in the loop around it. And putting another coil of wire in that loopy magnetic field will induce a current in the second loop of wire. This behavior, where we couple magnetic flux to create a different voltage, is identical to a transformer, and that's how we model it in a circuit. However, because these coils aren't tightly coupled like coils in a transformer, some magnetic field can escape. So the voltage ratio on them isn't given by the turns ratio of the two coils. Rather, it's given by some coupling factor, which may not be an integer. The two inductances that make up this transformer are called mutual inductances, because magnetic flux in one will always create magnetic flux in the other. Inductive coupling is super common, and it's used in almost all near-field communication and wireless charging. For example, your electric toothbrush is probably inductively charged, unless it runs off of AA batteries. You can get parasitic inductive coupling on a PCB if you make a big loop of wire. One classic mistake is to run a power supply trace on one side edge of a board on top copper, and then a ground return trace on the other edge of a board on top copper, and those two will form a big loop that couples magnetic fields into your circuits and throws them out into the world. One way that we measure electric and magnetic fields is by taking advantage of their coupling behavior. I've included a picture of a set of near-field probes on this slide. The leftmost probe measures E field, and it looks like a little stick that you could put in an existing capacitive field. The remaining probes are loops of various sizes that measure B fields, and bigger loops are more sensitive but less area specific. So in summary, electric fields can carry power or information in capacitive dividers. Magnetic fields can carry power or information through transformers, and near-field probes measure E and B fields using this behavior.